slightly faster. Let's see if there was, that was, the smaller one was towards you, I think.
So
It was sort of hinted on early, but then the interpretation sort of veered off. The radius and the mass do not seem to matter. Especially, I did these two, it was a tie. Obviously, different masses, different radii. These two were close to a tie. There are some slight differences there, but this is clearly heavier, more massive than this is. It's larger. Went to the other one, where I put the balls there. The thin shell sphere clearly was slower. And it does have to do with distribution of mass. So let's think about it in terms of energy first. If I have an object that is going to roll, it starts out with this, if I start it from rest, it has potential energy.
no kinetic.
Then as it rolls down, it'll lose gravitational potential energy, and that potential energy gets converted into kinetic. Well, if I think about it in terms of two different kinetics, I have a kinetic energy associated with the center of mass moving. That's the 1/2 mv squared. And I have a kinetic energy associated with its rolling. So I have a 1/2 mv squared and a 1/2 I omega squared. So those are my kinetic energies here. Let's go ahead and do it. mgh equals. I know that my moment of inertia is going to be some fraction times mr squared. So this is plus 1/2, some fraction, I'll just use the lowercase k, times mr squared omega squared. And that line right there is unimportant. I have an r squared omega squared here. That's just the speed of this object. So v equals omega r. So if I plug in v for that, I have mgh equals 1/2 mv squared plus 1/2 k mv squared.
Why don't we use n instead of k?
It was the letter that came into my head.
Okay.
So that's going to be equal to 1/2 mv squared k plus 1. Or 1 plus k, whichever way you like. So the bigger the fraction is, the smaller v is going to be. From an inertial point of view, the more mass I have towards the outside, the greater proportion of the mass going to the outside, the harder it is to get it to roll. So more energy is going to be spent into getting it to roll, and there's less energy left over to get it to actually move down the ramp. So the more the mass is spread out, indicated by that fraction, then the harder it is to start, and the harder it is to stop. Notice also, in doing this derivation here, r, the radius of the object, disappeared. So that's why the radius did not matter. Matter of fact, mass is going to cancel out. Mass doesn't matter. It's how the mass is distributed.
So what did you say K stood for?
K is that fraction in front. For a disk, it's 1/2. For a solid sphere, it's 2/5. For a hollow sphere, it's 2/3. It's that fraction in front of the formula.
So if
I
you
didn't
use-
actually catch the fractions. Can you go back a couple slides?
So K is 2/5, 2/3, 1/2, 1/12, 1/3. Stephanie, you were asking?
So in using this logic, using that logic, if you had like two spheres, same size, but one was like incredibly dense and the other was incredibly light,
Is it,
and you put it down a ramp, which would,
is it the same uniform density in each? As in, you said I have two spheres, one very dense and one not.
yeah.
If it's the same density throughout, so if this has the same density throughout the whole thing, and then I got another one like it with its own density, but it's constant throughout its whole thing, then it wouldn't matter. It's how the mass is distributed. If I had a solid sphere with a uniform density, and another one where most of the mass was on the outside and not much was in the middle, then with more mass closer to the outside, that fraction's gonna go up.
Is it?
It's gonna be slower.
So
What
it
does
would-
M equal and R? I can't.
M is mass,
What's the
R
word
is
above
radius.
it? What's the word above it?
entire,
Overall radius, that is
Entire mass.
thank you, entire mass.
Oh, entire.
so that fraction that would change that?
Yes, it deals with how the mass is distributed, not the density of the object, but how the mass is distributed within the object. We can also demonstrate moment of inertia with these two things. These have the exact same mass. The only difference is the distribution. So on this one, hopefully you can see it, I got two holes here and it's empty all the way through. Up here, it's dark. The red stick, it's empty up here, but it's darkened down here. So there's additional mass put into it. It's the same mass in the red stick, the mass is here. In the blue mass, the mass is spread farther apart. As I try to whip them back and forth, the red one with the mass closer to the center is much easier to get moving. The blue one, much harder to start, much harder to stop. So the entire mass does not matter, it's how the mass is distributed within each object. And for those of you who are thinking, yeah, this is great, but where's the real hardcore math? Don't worry, we'll get there. I do want to leave you with one more thought. Sort of a jumping topic, but it all connects. As I rotate this, it has an angular velocity. If it's an angular velocity, it has a magnitude and a direction, because it's a vector. What would be the direction of this angular velocity? Anyone?
It depends.
On?
Perspective.
It shouldn't.
So it's not like an instantaneous velocity?
Say it again?
It's not like instantaneous velocity where we find like the velocity of each point?
No, that's if you're dealing with linear.
Um,
If we were dealing with linear velocity, then yeah, we could do one at each point, but angular velocity, there's gotta be a way of doing it so it doesn't depend upon perspective. Because I sure don't wanna have to write, well, if you're standing at the front of the room, looking towards the back of the room, then it's spinning counterclockwise.
Where's the front of the room?
They came up with a way of doing this, and it's known as the right-hand rule. For those left-handed people, it is not the dominant hand rule. It is the right-hand rule. This clearly has an axis. It's rotating about some axis of rotation. So imagine you got your right hand and the thumb is the axis. The axis is running this way, so my thumb's either gonna point like that or my thumb's gonna point like that. This is a trick of how to do this. If you have some abnormal hand and your thumb can bend back so you're pointing towards yourself, that does not change the rule. So I want my fingers to curl in the direction that the wheel is spinning about that axis. So if I go like this, my fingers are not going the direction of the spin. If If I go like this, my fingers are going the direction of the spin. So the direction of the angular velocity is to the back of the room, or that way.
So it's
So-
not left to right, it's backwards or forwards.
It'll be the direction of the spin is perpendicular to the motion, which in this case would be backwards, forwards. If I did it like this, that angular velocity is up. Now, when I was first doing this, and you hopefully don't run into the same issue I did, when I was first learning this, I kept trying to figure out, in the first case of, wait, that's going to the back, what's going to the back? I could not picture at all what was going to the back. It is just a notation, it is a math thing. There is nothing physically going that way. It is a convention so that we say if the angular momentum is in that direction, no matter what the perspective is, you know it is rotating around like that. If I say the angular momentum or the angular velocity is towards the ceiling, well, if it's towards the ceiling, it's got to be rotating like this. So
So the hand's always pointed towards you.
okay, the thumb
Like,
is
well, the thumb could be pointed any which way, but this part, you have to be looking at your palm.
no. It's because if it's spinning like this, we'll do it the other way because of coordination issues. The thumb would point that way, and the fingers curl this way.
Oh, okay.
It's the direction of the finger curl. So that's angular velocity would be to the front of the room. And consequently, the angular momentum is towards the front of the room.
It's also just like which side of the axis is rotating counterclockwise.
Say it again?
It's also the whichever side of the axis where when you rotating counterclockwise.
No,
I don't know how to word it properly, but
you mean the way in which I push it?
or like it's pointing in the direction from where you have to be to view it from spinning counterclockwise.
Oh,
Because it's rotating counterclockwise.
I guess so, yeah.
So that could be another way.
There you go.
So like, would it say like it would be like all the way down, and then how would you do the different?
Well, I mean, if it were spinning like this, then that would be pointing that way.
So would it tell you which direction it's pointing?
If I said I have an object that is has an angular velocity of 5 radians per second I had, well, then whatever I had direction is. Perhaps better, rotating towards the ceiling at 5 radians per second.
Yeah.
Well, then you sort of picture it rotating towards the ceiling, which means that the thumb has to point up, which means it's rotating like that.
I'm just confused when it's not rotating towards the ceiling, when it's like side.
If it's rotating like this
Yeah.
or like that, well, then it's rotating, that's that way and that's that way.
But how would you know like without a demonstration? Like in a word problem?
Well, in a word problem, think about in the chapter 2, chapter 3, I said we have a car moving in a straight line. I didn't specify what direction, or it's moving in the I-hat direction. I didn't specify which way was I-hat. Same thing would be true here. I have an object rotating in the K-hat direction. Well, which direction is actually K-hat? Well, it doesn't really matter. Just hopefully, as we start doing the math parts, that it'll become clear. And if Zoom questions will come up again if not. But that does also introduce this idea of that we are now dealing with three-dimensional problems. We'll have an I-hat, K-hat, and J-hat, or usually in the order I-hat, J-hat, K-hat.
Could you go back one slide?
And on that lovely note, have a wonderful day.